We're live now, and over to you, Julia.
Yep. So my topic was to cover two chapters from our everlasting, well, not that much everlasting book, Agentic Design Patterns, which are, for some reason, they are split by several numbers, but they are kind of connected to each other, human in the loop and guardrails. So yeah, let's start. First, yeah, human in the loop pattern overview. So I like the picture that they shown. So without human oversight, the flow would be of any like interaction with agent would be user prompting the user query is wrapped up in prompt, then it's sent to agent. Agent makes some decision, which is some output action, and the results is presented to the user or affects them somehow. The idea of human in the loop is that agent is not autonomous anymore. So human can intervene with agent behavior in different fashions. So yeah, the core philosophy as the book stands it is that AI is augmentation rather than replacement, not autonomous agent. So in that case, the primary benefit is to mitigate risks of full automation, which may lead uh, to different problems. Yeah, and implemented that through the means of continuous learning from human input, leading to robust and accurate and ethical outcomes. And our book presents several types of human in the loop oversight when human monitors agent performance through the logs or dashboards. And based on that, very delayed fashion, like a reactive approach. Once agent already made some decision, then human can learn about that intervention. Then human can rectifiers can supply some missing data, and if agent does not know what to do next, then human can guide them. It may be feedback fashion when human behaves like a supervisor. So the feedback from the rather from the user, but from the human that oversees the system, tailors the behavior of the agent. Augmentation when AI works as a worker to provide some initial results, and human wraps it up, makes some final decisions. So it works like paralegal for a legal. And escalation when agent thinks that it is instructed to uh, escalate issues to the human in certain scenarios, then human operator interferes. Book provides several use cases which are uh, split like and emphasized by different features. So if it is high stake domains like healthcare, finance, or it is a very complex scenario, then we are not sure that independent agent can address all the possible ambiguity. Or if it is a changing environment, then continuous learning is needed. So they uh, showed several cases like yeah, healthcare and finance, for example, diagnostic systems, its ambiguity, fraud detection. It's also like high stakes, I'd say, domain. Content moderation, customer support, always also not clear how to address all possible scenarios. So once AI is not able to handle some basic scenarios, then some border edge cases are escalated to human moderators. In an autonomous system like self-driving cars, final control goes to humans for the case of unpredictable situations. legal and compliance. Again, yeah, as I said, AI can be a paralegal for a human expert in the field. And refinement of generative systems when it provides initial results and human editors or designers can take it from there. So it places some keywords, trade-off of scalability. If most of the cases we consider them to be border cases or sensitive cases, and they need to get to human operators, then it's always a bottleneck. We cannot scale human experts easily, so we would be restricted by that. And again, it would be the level of expertise. Would it be enough so humans also make mistakes? And yeah, how to scale it and I'll have a dependency on expertise. Also, privacy challenges. Once something is shown to a human, we must make sure that no sensitive information is exposed. I think I only learned, yeah, something that I learned from this book was human on the loop concept. I think it's in most of the cases it would be still considered human in the loop by the name, but they put it as a separate concept. So I like the picture that Notebook LM generated for me. So human in the loop is once agent is not able to sort something, then human looks at that particular one scenario and sorts it manually. And human on the loop is when human defines comprehensive policy or strategy, makes this strategic decision, and AI handles the immediate actions to ensure the compliance with this initially set strategy. So the examples they provided is when human financial experts defines investment strategy and the rules. For example, like 70% of this stock and 30% of that stock, and if something, then sell or buy something. And once the event unblocks this rule, AI just implements this action. So I think that it's in this case, AI agent is kind of should kind of have a very limited capacity in terms of what it can do. So it behaves in very isolated scope, and its behavior is very much ruled by this initial policy. Or another case they provided is modern call center. So there is a human manager who defined how to handle customers. For example, the rule, if there is an angry customer, by the tone of their voice, then direct it to the human agent immediately. And then the AI agent handling the communication and detecting this tone behaves according to this policy. Yeah, I think that was mostly it about human in the loop as connected to the book, and it takes us to the next chapter that is guardrails, or also known as safety patterns. Uh, it they set different stages when guardrails can be implemented, and what does it mean? So, starting from input validation, since we cannot limit with chat-like interfaces or with any free input from the user, we cannot limit what they input. So input validation is crucial here, and attackers can use it or different misuses of the system. Similarly, output filtering, we don't have control on like deterministic control on what LLM, which is the core of any agent, would give us. So this step is needed. Some behavioral constraints, direct instruction via prompts. So to LLM, hoping that it would behave like according to these constraints. So again, it's all about probability. So we try to make the behavior more and more predictive. Tool use restrictions that limits what agent is capable of, and therefore makes solution more secure. External moderation, if it is, we can we don't have to implement all the guardrails ourselves. If there are external APIs that can handle any of guardrail for us, we can use and call them via API. And human oversight, which takes us to what we just discussed with human in the loop. So yeah, primary purpose of the guardrails is to guide agent to prevent harmful, biased, and undesirable responses, which are like most of them is like misuses or intentional attacks or restricted uses, so unintended uses, unsupported uses. For every system, these each of these parts should be defined. And in many real life production scenarios, for example, in my work on any customer project, we have to pass RAI assessment to identify all of these scenarios and to make sure that each of the potential misuses is addressed with appropriate guardrail. Uh, what are the use cases for the guardrail? Yeah, yeah, probably the schema first. So the book puts it like that. So we have a user. There is instead of user prompt agent output, we have several layers of the guardrail. So might be input validation and sanitization. Defensive prompting is what I just mentioned when we direct guide LLM itself within a prompt how to behave and how to, like, in terms of misuse, which answer to return instead of following that input from a user. Output validation, so before we get output to the user. And uh, as I put it here, so um, it might need, depending on the case, it might need separate handling, separate API call, or our own custom handling, because we in particular case, we know what is the use case and what is intended use, which behaviors we want to restrict what is possible. And in many of the standard attacks, I would probably go with standard mechanisms that are already in place, like wrappers around LLM calls, services provided by different cloud providers to handle jailbreak attacks and so all the other attacks, because it's for the most cases it would probably be harder for the customer scenario, for production scenarios, to be up to date and to update these security guardrails yourself rather than rely on ever updated actual security handling from the main cloud providers. Yeah, use cases, customer service chatbots. We want to prevent offensive language, incorrect, harmful advice, off topic, toxic input. Content generation system. And we know how hard it sometimes gets to generate some totally harmless picture because of that. But you don't want to generate anything bad, but still the guardrails from ChatGPT, from Copilot, from whatever tells you that no, it violates some rules, but they probably maximize minimize false sorry, yeah, false positive, false negative. So they minimize the number, then it actually is able to generate something harmful, and sometimes we suffer from that. With legal and HR tools, we don't, and probably like with healthcare tools as well, it would be, we don't want to have to get systems to provide some definitive uh, advice rather than in ambiguous cases to guide users to licensed attorneys or doctors to ensure that they don't uh, to ensure that our system doesn't tell them incorrect advice, which would be then our responsibility. For HR tools, it's probably closer to our AI aspect. So to ensure fairness of candidate screening by filtering discriminatory language, and also I think here it's also about handling candidates with different backgrounds to reduce the bias towards particular features of the candidate, like nationality, language, whatever. Social media moderation to automatically flag posts containing hate speech, misinformation. For scientific research assistants, we want to make sure that no data is hallucinated and all the information that comes to through the assistant is well grounded. Otherwise, it might lead the researcher to wrong conclusions, which might maybe not directly affect somebody's life, but stop them for a long time and would just uh, put our reputation, like nobody would use the tool that provides that. And yeah, they kind of finalize it with best practices for AI agent to ensure modularity, observability, least privilege, and fault tolerance. Transactional system similar to database when we can commit and roll back, like operating checkpoints of the states of the system. Modularity and separation means that we want to rather have plenty of specialized agents rather than monolithic omni agent that does everything. Andre, do you want to say something? No.
Oops, no, no.
Oh, okay. Structured login to, yeah, observability can feed us ideas of how to develop the system further if it drifts with time. Least privilege means that every agent in the system should get absolute minimal permissions that are required for the task. Integration of principles of fault tolerance, model design, deep observability, and strict security. So all four of them should be essential. And yeah, move to get to ultimate outcome, move from simply functional agents to robust, audible, trustworthy systems. I think, yeah, that's it from my side. I I think it was rather similarly probably to our feelings about previous chapters. I had feeling that it's more was common sense. Maybe we just know that too well, but not that it was any particular point here was an eye opener, but it was good to just to have some system behind how we implemented guardrails and how human in the loop point can be treated in particular production use cases.
For the guardrails, I think author also missed quite important use case, which is jailbreaking. because there are ways to break almost every model, and there are groups and approaches and research how to do that, and these guardrails should also ideally prevent from the jailbreaking.
Mhm.
Another thing.
I think they had it inside the prompt. So in the very first case, practical case that they provided for guardrails, it was like detect jailbreak. Jailbreak is something something, but it was already like in practical task. But I agree, they didn't emphasize that
Yeah.
much.
For the human in the loop, there was a research recently stating that for the most people, it doesn't matter if response came from the LLM or from the human expert. If people see a nice written text, they just don't
Hmm.
care. And that is a problem in my opinion, because um, we have to apply a lot of efforts into reviewing these LLM responses. This looks so good that we just don't care if they have any errors or
Yeah.
mistakes.
Actually, I'm preparing for the scenario when we are creating a copilot in healthcare sphere. So it's uh, very sensitive case. So it should not be getting any mistakes ideally. So human in the loop there is must. And we were thinking like how we can ensure that that human healthcare professional don't automatically accept what they get. And I think we have a list of mitigations, and one of them was to make sure that they have to accept every deviation. So to like every deviation from standard. So we as humans, we had difficulty to read big text. And as you said, if it is well formatted, we just believe it and
Yeah.
scan it and agree, and don't want our brain to think too much. But if there is a like your standard patient case, and you know how you would handle it. So if in that case you have emphasized pieces that are deviations from standard, like git diff, so you don't review the whole file from every time it gets committed. You only see the difference, what is specific about that case, and be if it is presented clearly. So I think it starts a lot connected to design, UI UX design, in making sure that for human it would be real oversight rather than click click click. Yes, I agree.
Right. Yeah, and I also think because this is really complicated and very difficult to build a proper human-in-the-loop solution with a nice UI, etc. Well,
Hmm.
most of companies just use an LLM as a judge for human-in-the-loop and for the guardrails. And I think it makes sense probably if you have some specialized LLMs which and their task is basically just criticize all the responses coming from
Hmm.
another LM. That might be useful, and looks like research proves that.
Yeah. I actually experimented with a bunch of agents, calling one of them Devil's Agent, as somebody recently posted and suggested. And I liked how it behaves, even for coding tasks, how this swamp of agents operated. So, uh, yeah, I think it's in very sensitive cases like terminal patients or something like that. You never can fully exclude human in the loop, but you can uh, minimize the involvement of the human into some some tasks that can be handled with LLM as a judge approach. So to delegate as much as possible to AI and to minimize minimizing the amount of information that comes to the human,
Right.
you allow human uh, to have a big attention span to actually focus on what is crucial. So
Yeah. Yeah. All right. Thank you so much.
yeah, thank you.
Okay, then. I guess let's go to the yeah, where's the video? Next
Stop
chapters
sharing.
then. Let me quickly share my screen. And you should see my screen, guys.
Yep.
Lovely. Right, so now to RAG, A2A, and resource aware optimization. And I'll try to be concise because I think that, like, probably RAG is fairly sophisticated topic, but A2A and resource aware optimization, in my view, they're fairly simple, especially A2A since we kind of covered MCP already in the previous meeting. So, like, anyhow, I'm getting ahead of myself. So let's go through the slides one by one. Um, Basics. RAG. To understand RAG, we need to understand uh, how information is encoded. And information, um, well, any kind of information on a computer is encoded via numbers, right? And when we're talking about machine learning and specifically deep learning, usually, well, not usually, like, I don't know any other alternative to encoding text as something other than a vector. And the vector is basically like you can think of it as an array of numbers. So basically, we have a magical box that translates a phrase "I love cats" into a list of numbers, and we call it a vector. And we can train our so-called embedder, which is just a neural net, to look for certain information, similar information in our data. For instance, here I have I love cats and I love dogs, and they both marked as 1. And it means that I want to train my neural net to classify. Well, probably should have added some 0 entries to kind of highlight the difference. But, well, we can see it as an example of how I can try to train my neural net to classify whether, like, whether this in this sentence that we putting through the neural net, uh, we have some sort of a I don't know. We can try to classify love for animals, so we can have a data set where each one of the entries where somebody expresses a positive attitude towards animals marked as 1 and everything else is 0. And in this way, we would have two vectors for I love dogs and I love cats, and they'll be pretty similar to each other. They will be slightly different because cats and dogs, they're different, well, different, well, not species, well, different kinds of animals, right? But still, it's kind of loving animals. So it's kind of we pushing network with our data, without annotation, to treat these pieces of data very closely to each other. And you can see it in this example embedding that came just from my head, that we can see that it's pretty much the same numbers. We have difference only here and here. And we can imagine it as two vectors in space that lie pretty close to each other and they have a very small angle between them. And the reason why I'm talking to you, like I'm telling you all of this, is that when we embed certain information as a vector, as this list of numbers, we can rank all other information, well, chunks of information that we have in our database, so like anywhere else, by this similarity. like we can have actually multiple ways of how we can find similarity between two vectors. And probably like thinking about angle is the most natural way of how we can think about similarity of two vectors. So here, um, imagine that you have 1 billion vectors and you want to find only the ones that kind of leave that have the smallest angle to the vector that you're querying with. So this is roughly the idea. You can just find the angle between two vectors. And in real world, so that was basically the idea of a vector database and how you can extract vectors from the vector database by their similarity. You have a target vector, you have a gazillion of vectors in your vector database, and you just rank all of the vectors in your vector database by some similarity score. And the most intuitive similarity score would be so-called cosine similarity, or like you can just think about it as an angle between two vectors. So if the angle is small, the vectors lie close to each other, and well, your database is going to return them first. So it's a sorting criteria. Well, now, um, here comes a question. What do we do if we have 1 billion data points? If we, let's take a look at this vector, for instance. It's a fairly low dimensional vector, and in real world, we would probably have a higher dimension, meaning that we would have many, many more numbers in this array. Maybe 100, maybe 200, maybe 700. Who knows? It depends. It all depends on how much data, how much expressivity we want to encode in this vector. And the natural way of how we can try to find how closely two vectors live to each other is by calculating their dot product. And long story short, the dot product is going to, like, via some various mathematical tricks, it's going to give you the angle between two vectors. But essentially, when you calculate a dot product, we pairwise multiply each one of the entries in the row. And since we have, for instance, 100 entries in each row, there will be 100 multiplications, and then we sum all of the multiplications. There will be another 100 sums. And this roughly gives us, well, 200 operations, at very least, right? And then if you have 1 billion vectors, you face a problem, because you're facing 100 billion, well, 1 billion multiplied by 200, right? So it's 200 billion operations to do a single query of fetching the data from a vector database. And well, probably, well, my gut tells me that it's going to be very slow, and it's only fetching, right? After you fetch, you also have to find, you also have to do the sorting, you also have to do the ranking, because like finding only the similarity score is not enough. You also have to kind of identify the threshold above which you're going to return the data. So it's not going to work at scale. So how do people usually approach it? What lives inside of the RAG database, really? Inside of the RAG database, one of the approaches that you can take is you can think about it as some sort of divide and conquer stuff. Say you have this 1 billion vectors. Then, and you embed all of these 1 billion vectors initially, maybe in some background job. Once you do that, you can pick a feasible number of groups that you can have. Say 100. Querying against 100 vectors would be much, much better than querying against 1 billion. And then, once you pick a number of 100, you run a so-called k-means clustering algorithm. It's a smart way of, well, basically naturally finding groups within this initial 1 billion vectors that live close to each other, and you use this 100 as a hyperparameter that identifies the number of cluster that you want to find there. I'm not going to describe the k-means clustering algorithm here, but the idea and the intuition is that there is a way, like there's a black box that can give you um, a median value for a fixed number of clusters, and it automatically, magically finds the best cluster distribution. Well, small caveat that with different starting points of the search algorithm, the result is going to be different, but I don't think it matters really here. What you really have to remember is that you have a way, you have an algorithm, existing algorithm, that can find natural clusters within your data, and you provide a number of clusters that you want to find. So you identify 100 clusters. Well, you actually here, like you identify that you embed all of this data, and you identify 100 clusters. I here depicted like only 3 of them. And then you have a mapping. Now you have 100 clusters. Each one of them has a mean embedding for all of the vectors in this cluster. And then when you do the initial search query, you query only against the groups. So what you query against, not against these embeddings, but you query against this grouped median embeddings, only against 100 embeddings. You find the groups that you want to target. And then once you, well, identified maybe 1 or 2 groups that you want to target out of 100, only then you go deeper and you query inside of those groups. So this is basically the divide and conquer algorithm for vector similarity. And it works well at scale. When you want to kind of find similarity in meaning or in like semantics, so like maybe you want to find something like a phrase similar to I love parrots, or I love how my cat purrs, right? But here's the problem. These embeddings, they don't allow you to do exact word search. For instance, if you go to Google right now and you try to Google something like, I don't know, some abbreviation like pretty much anything. We can think about even like this specific, like little ML book club, right? Well, it's not Google, it's my presentation. But here you can see that in my presentation in the PDF, it looks for exact word match. And with embeddings, we wouldn't have that. So usually, what we have in real world systems, we have 2 algorithms running in parallel. So we kind of undo them simultaneously. So in one stream, we do this kind of meaning similarity search using vectors. And on the other hand, we have the exact word match search. And how we can do this, how we can rank the documents against the exact word match. Uh, well, I mean, like, say you try to search for cat, you'd probably have a gazillion documents mentioning cats. How do we rank them? How do we pick 100 documents out of, I don't know, 1 billion documents having mentioning cats? And here comes another like well-known algorithm of how you can do it intuitively. So imagine that in each document, well, you tokenize each document, like right here in the picture. You kind of tokenize and clean all of the words in the document. You also remove stop words, so-called stop words, like the rubbish stuff, like that. Basically, the words that don't contribute to any like meaning, don't convey any meaningful information, and you got left with a set of words, meaningful words that contribute to the meaning of your document. Then you calculate the turn frequency. How often in this doc you see this word? against the set of entire words that you can think of. And you get this DF score, term frequency. But then here comes another problem that how can we find a word that uniquely identifies a document? Because some words, I don't know, probably home, love, human, like common words, are going to be, well, you're going to see common words much more frequently in all of the documents than any of the rare words. And they would dominate naturally over the rare words. And then your ranking algorithm is going to suffer because of this, right? So a clever idea is to use, well, not calculate not only term frequency per document, but across all of the documents, calculate document frequency. So like it's the next step in this diagram. And basically we calculate how many, well, how many times we see this, like in how many documents we find this word, and then we calculate the inverse score for the document. Well, for across all documents. So like cat is seen only in one document, but dog is seen in two documents. So the inverse score for the dog is going to be, well, let's see. I think it's going to be lower, right? In the final result, because we multiply term frequency by the inverse document frequency, it naturally decreases the weight of the words that are not unique to the document, and all you're left with, well, not all you're left with, but most of the weight is attributed to the words that uniquely identify your very document. So rare words that you see less frequently in other documents get more weight, and they kind of classify or identify your document. And that's the whole idea. Basically, it's the foundational idea that lies underneath the, I think it's BM25 algo or something like this. It doesn't really matter, but it's roughly the same with a few bells and whistles on top of it. And here's a heat map that, like real world heat map that you can find if you try to build the visualization of this TF IDF thing. So like across multiple documents, you have the multiple scores, and that gives you a natural ranking. So for instance, when I search for computers, I can immediately see that document 5 is the only candidate across all of the documents that we have. And if I search for, well, let's see, well, probably not the best ranking ever, but well, if we take a look at document 5, we can see that it's described by computers and different in like in much better detail than it described by apples, for instance. And this gives us a way of how we can find documents by the exact word match. And then in the end, kind of you run both algorithms, and then in the end, you feed the results from both algorithms to the final neural net, and that gives you the final ranking. It doesn't, like, the final step doesn't matter as much, and it's not as interesting as understanding the intuition behind running two algorithms in parallel. And the final thing that the book mentions is graph rag working scheme. Well, the idea is that on top of the rag that you have, when you find the documents, you can also have a graph, and you can try to find the relations between documents. And when you find your final ranking of the documents that you want to um, return, you can also explore the graph and maybe return a few closest neighbors, or maybe if you have kind of directional relationships, you can use this information as well in the ranking algorithm. And the final scheme that we had in the book is that we have a query, we embed this query, we have external document that's split in chunks, then we do this similarity search across multiple embeddings, And now, as we know, it's not only a vector database. Like, vector database is only part of a sophisticated RAG system. So, like, we also know that on top of the vector database search, we can do an exact query search, join these results together, and get the final response that we embed into our LLM for um, synthesis of the final output. All right. So this was probably the most complex part of today's presentation. The rest are fairly simple. So agent-to-agent protocol. Well, we already know about MCP, right? It's you provide a entry point for your model, well, for your client, to look up the definitions of all available tools, and then feed the tool definitions back to the model in the context. Roughly the same idea. But now, instead of the tools, you have another agents that you can talk to. So, well-known URL, well-known schema, and this schema, like your client can connect to another agent and query what the agent is capable of, what operations it supports, and feeds it back to your source agent and puts it in the context so the source agent can use it. And here's the synchronous request example. We can see that, well, we sent some task with some data, and we expect the reply, well, within some reasonable amount of time. So it's basically request response kind of um, interaction. What is different compared to MCP? So this stuff, it looks a lot like MCP. But this stuff, this is something that cannot be handled by MCP. So we send task subscribe message. And what it means that now other agent is going to notify us when they, well, when they see any updates for the currency rate. And A2A protocol at its foundation supports synchronous request response, asynchronous polling, streaming updates, and push notifications. And to my best knowledge, the first part, it's roughly replicating MCP, nothing is different. But what is really different is that now we have some state. So now we can do asynchronous polling, and now we can ask other agents to be proactive and update us when they see something. So we assume that this other agent has long living state. It's not like just a tool that we can call and get the results back. And we can also get push notifications back from that agent. So I'd say the difference between MCP and A2A is that MCP is naturally a master-slave relationship, and A2A it's kind of a master-master relationship. When you preserve the state of you can preserve the state of communication between two agents. And the last bit, resource-aware optimization. Um, well, I think the author wrote a lot of words, which we can compress to basically two statements. Use less data. And we've just covered RAG. And we covered like not the naive RAG implementation of like, hey, we just find similarity between two vectors. We covered how we can use two different algos and kind of how we can use ranking across two different algos and how we can actually reduce the amount of data, right? We do the grouping and we query only within the groups. So we kind of covered how we can use less data. Another idea is to use smaller models when possible. And it all boils down to this schema that whenever you want to do something that can be expensive, for instance, you have a big, very, very big model, like 1 trillion parameter model, and everybody wants to use this model on every request. And but that's what users want. When we are a provider, we want the opposite. We want to serve as many requests as possible with our small model that we distill from our big model. But at the same time, we want to keep our users satisfied. So how do we do this? And probably the most natural approach and the most simple approach that still works fairly well is to route all of the requests through the small model. Well, some sort of a classifier, small classifier. If the classifier is confident enough, like if the output of the small model has very high confidence score, and we can use different metrics for confidence score, but we can imagine standard entropy, for instance, for now. Then if small model is very confident, we just feed the output of the small model to the user straight away. But if the small model, and we can set the confidence score like threshold to be very high, so like we accept only very confident responses from the small model and route it to the user, so the user doesn't see the difference. But if the confidence score is below some very high threshold, then only then we reroute our request to the big model and pass the output of the big model to the user. So roughly, this is the main scheme of how we can save a ton of resources on computation. And that was really it. Do we have any questions?
For the RAG, I'm curious if you had any experience building such systems and what is your take on the chunking strategies? Because in my opinion, this is the most difficult part.
Nope, didn't build them.
Okay.
Thank you.
I did.
Yeah, Yulia, over to you.
Uh,
You did.
yeah, so well, I think we started with RAG. Even like I was part of outsource RAG experiment accelerator in Microsoft. So uh, we added like plenty of chunking strategies, plenty of indexing strategies, so that anyway, in the end, it comes to you try all the possible variety, you check the metrics, KPIs, and then you select what works for you. Also, on top of simple reg, then uh, you consume plenty of documents, you chunk them logically, chunk them by particular size and paddings, whatever. You can also build something hierarchical. So I also had an experience of building knowledge graph, which would be the nodes would be documents and parts of the documents, and uh, they would be connected through the entities and relations between those entities. So that helps that serves as an alternative to indexing. So instead of and then when you build knowledge graph, so in that case we used Neo4j graph, so you can it naturally provides opportunities to search by keywords, by vector, or hybrid. So that allows you to use your indexes to identify the initial nodes, uh, documents that are closest to your search request by the uh, semantics, similarly to RAG by embeddings or by keywords, depending on your task. And given this initial number of nodes, you can then add your query to traverse graph to expand it to give you more context. For example, if you chunked your big documents in parts and you identified one of the parts as a potential source of answer for your query, then probably previous chunk and next chunk are also good candidates, or maybe the whole document. Again, yeah, it depends on the use case, but I found that for complex scenarios with when there is some predefined schema between entities for something like medical domain or legal domain, so you already know which entities might be there and what is the relations between the entities, and you can naturally embed this knowledge into the RAG-like, RAG-based system that you have, and yeah, knowledge graph in this scenario when your data is already somewhat classified and somewhat structured works.
Got it. Thank you. TLDR is that it is not an easy task to build a good
And
RAG system.
it's it, I think it depends. I also I
Okay.
think yes, three weeks ago, a month ago, I built a super tiny rag for myself to get prepared for life in the UK test, because standard explanations is like X did Y. And like, okay, thank you, but that doesn't help me to memorize the content. So I built it for, I extracted entities from the question and correct answer. I searched by them in Wikipedia. No legends, just like simple requests for top three article summaries. And then I used that context as the in as the context uh, to 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 take the well to build the answer from. So it's not I probably so it is RAG because you don't ask LLM with no context, right? But it was super simple and maybe trivial scenario when I would provide the context within each query just uh, as a chunk of the articles found by keywords. So it it
Right.
is RAG in like logical sense, but it's very tiny one. So
Okay. Thank you.
Right, and we ran out of time, so yeah, thank you guys for coming today, and we'll see you for the last meeting on Friday to wrap up the book. And well, yeah, have a good day
yeah,
and see you on Friday.
yeah.
Cool.
Thank you.
Thank
See
you.
you. Bye.
Thank you. Bye.